Okay, welcome back to Chapter 18. We're going to learn in this little lesson about some interesting phenomenon and applications that relate to refraction. And that may look like a cookie to you, but in fact, it's just a mirage. We're going to learn about mirages. That was a real cookie, and they're very good, by the way. Um, by the way, Prosper, if you're watching, I'm presuming it's got to be about like 5 p.m. or later. Okay, so Mirages, here's what's going on. Has anybody ever driven down Interstate 5, really hot day, and you look down the road and it looks like there's a puddle of water in the middle of the road, and then when you get up there, of course, there isn't. You see reflections of cars coming at you. Well, this is all part of a mirage. And as it turns out, the speed of light changes with temperature, and it is faster in hot air than in cold air. Okay, that's point one. Point two, the road is hot because it's black. Remember, black absorbs more of the radiant energy from the sun. So, air temperature at the road surface is higher. Surface is higher than up in the air. This causes light to change direction. If you recall, when you change media in different temperatures of air, there are different media, it will make the light change direction. Okay, this is refraction. Okay, so let's assume that you're over here and you're looking at the infamous arrow that we always look at. Okay, this light is going to travel from here. It's going to go right into your eye, and you're going to see the arrow. Well, as it turns out, as the light also, let's take a light ray coming down, it's going to go through strata of temperature, right? And so, in fact, if you draw a normal, the light ray starts here. It's going from slow to fast, so it's going to bend away from the normal, away from the normal, away from the normal. You can do that. It's distinct points, but in fact it's a continuum. And so this light ray is going to bend away. Okay, it's going to hit the road here, and some of this is going to reflect back in your eye. And it will do the same thing if you draw the strata of temperatures. It will go then from fast to slow to go towards normal. You see that it'll bend back up into your eye, and so what your eye sees is the real object, but it'll also see this other reflected, after it's been refracted, light ray coming into your eye, and you will see an image that is upside down, and it is a mirage. And what your eye says, well, if I'm seeing something there, there's got to be like a puddle of water there to reflect this. And so you see this puddle of water. Okay, this is the mirage. This cookie, mirage to you, but not to me. Okay, now let's talk about something really, really useful, total internal reflection. Let's draw a boundary here. And we're going to draw a whole bunch of normals to the boundary. Look like this, like this, like this. Okay, let's say you've got, this is the incident side over here, and this is the refracted or transmitted side. Let's say we've got a light ray coming in. It's theta I. Now, let's say this is slow and this is fast. So this guy has to bend away from the normal. No problem, right? Okay, well, let's increase theta I a little bit. Well, this has to bend still even more away from the normal. Well, let's increase it even more. And you're going to see it bending even further away. What if we made it go to the point where it was at 90 degrees coming out? This is now the angle of refraction. This is called the critical angle. Can you see at this point, no more light will leave this surface. Now, as you know, also some of the light will be reflected in, and the angle in is equal to the angle, the angle reflected in will be the angle of incidence. But at this point, all of the energy now is kept in. So if I am at any angle above the critical angle, so here's my normal, and let's say this is theta I greater than theta C, all of that light will be reflected in and nothing goes out. That is total internal reflection. And the most obvious, oh, this critical angle, by the way. Oh my goodness, I just realized you weren't seeing me draw all these. What a horrible teacher. There they are. We increase the angle of incidence step by step by step. This critical angle is the angle theta I, which is equal to theta E, so say theta critical, so that theta R is equal to 90 degrees. So what is the sine of 90 degrees? That is 1. So n sub I sine theta critical equals n sub R. And remember, these are the indexes of refraction for the incident side and the refracted side. So the critical angle is simply the arc sine of nr over ni. Beautiful. Okay, fiber optics are the biggest application. You introduce light here, and you introduce it at a angle such that it exceeds the critical angle, and this is the so-called core. Then you have a cladding on the outside which has an index of refraction less than the inside, the core, because this has to be from slow to fast. So this typical fiber optic is two types of plastic or glass, and the inner core has n sub I is greater than the n sub R, or the cladding. And so you make these two types of glass. You introduce, and this then uses total internal reflection, you introduce the light at an angle of incidence greater than the critical angle, and you will get a fiber optic cable. I'll give you a link actually to go look at some of these, but basically think of having surgery in your body and they don't want to cut you open completely, so they just poke a hole and put a little tube in there, and that is the fiber optic cable. They can then put light in, they put a camera in, and then of course they can put some tools in. So this is the fiber optics. Okay, let's talk about one other interesting phenomenon, and that is rainbows. First of all, let's go back to what happens with white light in a prism. It's called dispersion. So we have our light coming in. Here's our normal angle, and it's going to go from fast to slow. So it has to bend away from the normal. So this is theta I. Towards the normal, because it's a fat science teacher. So it's going to go down like this. And then it hits over here. We got another normal here, and now the light has to bend away because it's going slow, fast away, and it goes down like this. Well, as it turns out, red is slower than blue in this medium. And so what ends up happening is you get different amounts of bending. And red gets bent less than blue, and so you get Roy G. Biv. And that is the prism. That's the separation of colors. All right, well, let's imagine now how a rainbow would work. This is a droplet of rain in the sky, water. That's what clouds are. They're just moisture. And you've got the sun over here behind you, like this, and it sends in white light. Okay, as we know, that is made up of red plus blue plus green, all the different spectrum colors, just like up here at the prism. All right, you draw a normal to the boundary, and what you find is red gets bent a little less than blue. Okay, now off the back of the So you get refraction here. Off the back, you get some light that goes on through, and you don't worry about it. But some of this light gets reflected back internally. And the angle coming out here is going to be the same angle that it bounced in at. So you're going to get blue up here and red down here. So this is red, this is blue, this is blue, this is red. And then coming out, it's going to get bent down. Okay. If your eye is right here, you're going to see red. Now, there's another raindrop down here, and down here, and down here. This one will come out, and this will send the blue into your eye. And so when you look at a rainbow, you always have red, this is red, sorry. You always have red on the top and blue down below. And that's because of the different speed of these two colors in the water and causing this refraction at different levels. And so this raindrop will show red, this one will be blue, and in between you'll have the whole spectrum. So whenever you see a rainbow, first of all, you always know there's a pot of gold at the end of the rainbow. Here, we'll put the cookie down here for my pot of gold. You'll have red on top and blue on the bottom. Now, if you see a double rainbow, I don't know if anybody's seen one of those lately. Sometimes this can keep going around. So some of this energy will get reflected back again and it'll go around. And when that happens, the second rainbow, the double rainbow, will have blue on the top and red on the bottom. And it's much less intense because most of the energy has been used in making the first one. So there you go. We covered mirages, dispersion, fiber optics, total internal reflection, and rainbows. By the way, there is a really good diagram in the book on page 498 of the rainbow phenomenon. They also discuss dispersion and fiber optics. So there you go. I'm done. My wife is making, oops, don't say her. She started to make lunch, so we'll terminate it for now. So long, everybody. Oh, hey, you guys, make sure you show up on time next time.